we have some example of a semi-infinite solid, and we start with exercises of numerical applications. Okay, the first one is also in this case you have the text of exercises on the Aula web. You have a PDF file with the texts of the exercises. In this case, we consider a copper sphere. Wait.
Which exercise, please, sir, with the...
The exercises are related to lumped system analysis. And wait, okay. Okay, the copper thermal conductivity is 380 watt divided meter Kelvin. We consider also a water drop. The thermal conductivity of water is different and is equal to 0.6 watt meter Kelvin. Okay, we immediately evaluate which is the characteristic length of the phenomenon if we consider a spherical shape. So V divided by A is equal to 4 divided by 3 by R23 by 4 pi R4, and the ratio gives us R to 3. So the characteristic length in the Biot number to be inserted in the Biot number is R divided by 3. We imagine to locate both the cases in a fluid with H equal to 38 watt square meter Kelvin. We have to estimate for which radius we have, okay, we can apply the lumped system analysis. So this one is the question that we have to answer. And we know that to apply the lumped system analysis, we have to obtain the Biot number less than 0.1. So the solution is for the copper, I have that the Biot number is equal to 38. Okay, the Biot number is HV divided by A divided by K. So is equal to 38 by R3 divided by 380. Ok. Quando partono poi non smettono più queste notifiche. Ok, and if I solve for R, I obtain that R must be less than 3 meters. Okay, to have, wait, I write better. Okay, if I consider a copper sphere, I can apply the lumped system for a radius that is less than 3 meters. That means that in my mind, when I think about a lumped system, I think about a small body. But if the thermal conductivity is I, as for the copper, the system can be considered as a lumped system also for big value of a radius, in this case is enough to have a radius less than 3 meters. For the water, I have that the Bayeux number is again equal to HV divided by A divided by K equal to 38, that is H, R3, R divided by 3, and 0.6 must be less than 0.1. And in this case, the radius of my water drop must be less than 0.0047 meters. So less than 5 millimeters, more or less. If the radius of the water drop is bigger than 5 millimeters, the system can't be considered as a lumped system. So this is only a simple example, nothing particularly difficult, but to put numbers, to put properties inside the definition of the Bayeux number allow us to estimate the size of the different system that can be considered as a lumped system. It's okay for all of you?
Yes.
Ma'am, I have a question.
Okay. Please ask to me.
Yeah, well, you said here in the water droplet that the radius of it should be less than 0.0047 meter.
Yes.
How do we, come to that conclusion that it should be 0.0047 meter? I mean, how do we get to that?
Okay, because I impose, I have to impose here that wait, because why I have to impose that the Bayeux number is less than 0.1. To apply the lumped system analysis, Bayeux number must be less than 0.1. This one is the Bayeux number. If I assume that it is less than 0.1, I solve for R and I obtain that for me R must be less than 0.0047. It's clear now?
Yes, thank you.
Okay, you're welcome. Okay. Second example. Wait. And in this case, I consider as lumped system the junction of a thermocouple. You know that what is a thermocouple? Is a system, is an equipment able to measure temperature. And we have the junction at the tip of the thermocouple. We have a junction of two metals, and the junction is in the order of 1 millimeter. So we want to approximate this junction of a thermocouple as a sphere again, with radius no, diameter. Yeah, okay. The data is provided in diameter. D equal to 1 millimeter. So it's a very small sphere. And the following properties. K equal to 35 watt-meter Kelvin. And density rho equal to 8,500 kilogram each cubic meter. And specific capacity equal to 320 joule kilogram Kelvin. I open a window, please, because now sono solo io. Okay. And Okay, the thermocouple measure the temperature of a gas stream. Yes. Sorry? C is the thermal capacity, calore specifico. And so the thermocouple measures the temperature of an air stream that has AH, coefficient of convection, 210 watt square meter Kelvin. You know that when I use a thermocouple to measure temperature, I have to wait a certain time interval. Why? Because the thermocouple measures the temperature of itself. So what is the temperature that the thermocouple measures? The temperature of the junction. So if I want to measure the temperature of a gas stream, I have to put the thermocouple inside the gas stream and wait enough until the junction arrives in thermal equilibrium with the gas stream, and so the temperature measured by the thermocouple is the same of the gas stream. Is clear this point? So the thermocouple measures the temperature of its junction. If I put the thermocouple in a gas stream, at the beginning, the temperature is not yet at the temperature of the gas stream, the thermocouple. I have to wait up to the thermocouple junction, reach the thermal equilibrium with the gas stream, and assume it's the same temperature. At that moment, I'm sure that the temperature measured by the thermocouple is the thermocouple of the gas stream. And if I consider that this junction of a thermocouple is a lumped system analysis, the problem asks me which is the time interval after which the delta T between the thermocouple and the gas assume the 1% of the initial value. Okay, it's written also in the text of the exercises. Which is the time interval for which the delta T between the junction and the gas reach the 10%, no, the 1% of the initial delta T. Of the initial, it's not simple to write here, initial, it's better the blackboard, but the initial delta T. So, at the beginning, the temperature of a junction will be, for example, Ti. If you go back to the theory of the lumped system, at the beginning, the lumped system is a temperature Ti. Then is located in a fluid, in this case we have a gas stream, but has a different temperature, T infinite. After a period of time, according to the law of the lumped system analysis, the temperature of the junction changes towards the temperature of the gas stream. The delta T between the junction and the gas stream decrease from an initial value, that I can call it init, to a value that is 100% of the initial delta T. At the beginning, the difference is the maximum difference. Then this difference decreases and reach a value that is 1% of the initial one. For which time this delta T reach the value of the 1% of the initial delta T? This is what we have to evaluate. Okay? And if you have finished, and if you understood, I can change. If nobody say nothing, I assume that it's clear for all of you. And yes, thank you. Thank you for the feedback because it's important. And okay, critical characteristic length of a phenomenon, V divided by A. Again is D divided by 6 or radius divided by 3, as previously calculated for the other case, for the other example. And in this case, I calculate it knowing the diameter, and is equal to 1.67, but multiply 10 to minus 4 meter. And Biot number is equal to HLC divided by K. For me is equal to 210 but multiply 1.67, sorry, anche this numerically in English, divided by 35 equal to 0.001, that is less than 0.1, okay, that means I can apply the Lampert system analysis. So, first of all, before starting the calculation, I have to check if the situation, the system that I have to study, allow me to apply the theory of a Lampert system. And it's okay, I calculate the Biot number. If the Biot number is less than 0.1, okay, I can approximate it with a Lampert system. And I want to obtain tau, okay, tau for which T of tau minus T infinite divided by T I minus T infinite is equal to 0.01. This one is nothing else than 1%. Because the question was for which tau the unknown is tau, for which tau the temperature difference between the temperature of the body, T tau, minus the temperature of the gas stream is the 1% of the initial delta T. The initial delta T is the initial value of the temperature for my junction minus the temperature of the gas stream. And I calculate the constant in the exponential formulation of the Lampert system law, that, if you remember, is 1 divided by tau 0 equal to HA rho CV equal to H divided by rho C characteristic length equal to 8,500 by 320 by 1.67, that multiply 10 to minus 4, and I have at the numerator 210. And this number gives us 0.462 second minus 1. This one is this constant. And if you remember, the law that regulates the behavior of the lumped system is T tau minus T infinite Ti minus T infinite equal to E minus tau 0. This one must be, for me, 0.01. 0.01. That is this one, okay? This condition is the same as this one. I solve for tau, and I obtain that tau is equal to 10 seconds. Okay, in this equation, the only unknown now, because everything is known, the only unknown is this one, tau. I solve the equation for tau, and I obtain that the temperature difference between the junction and the fluid reach the 1% of the initial value after 10 seconds. It's an important information because it means that to have a useful measurement by my thermocouple, I have to wait at least 10 seconds to have an error that is less than to have an approximate difference that is nearly 1%, at least 1% of the initial delta T. Obviously depends on the delta T that I had at the beginning, but can give us an idea to how I have to what I have to wait to have a good measurement. Ok? Va bene, tutto chiaro qua in classe? Bene.
Professor, could you please explain the result? I can't understand.
Okay.
I'm sorry.
Okay, so wait, listen. And from the mathematical point of view, nothing difficult. I have checked at the beginning that the system is a lumped system. Then the problem asked me how I have to wait, which is the tau value. Tau is a time value that I have to wait to obtain after this tau time a delta T between the junction of my thermocouple and the fluid that is equal to the 1% of the initial delta T. Okay, the initial I write here again at this point. T of tau minus T infinite equal to 1% of what? Of Ti minus T infinite. The initial delta T questo is this one. Delta T initial is this one, okay? 1% is 0.01, and the unknown that I want to evaluate is this one, tau. The tau for which the actual delta T is 1% of the initial delta T. And I use the law for the lumped system, that is this one, in which I have directly this ratio that is exactly what I want to estimate, that must be equal to 0.01. So, this is the law for a lumped system in which I have tau and tau 0. I have calculated here tau 0, 1 divided tau 0, but it's the same. That means that now, for me, here I have only the unknown, that is tau. I solve this equation for tau, and I obtain tau 10 seconds. It's more clear now?
Yes, Professor. Thank you.
You're welcome. Now we go to exercises associated to the semi-infinite solid. So in the text, you are now in the following small chapter that is semi-infinite solid, and we have in particular this problem. We have to determine the minimum depth at which we have to locate a pipe into the ground when I have the initial condition equal to 15 Celsius degree, and due to the ground surface is covered by snow, after 3 months the temperature is equal on the surface equal to minus 10 Celsius degree. So I can now write something for you, because I have exercises here in my paper in Italian. I have to translate in English, and so the unknown is the minimum depth. We have to find this minimum depth at which we have to locate a pipe. For a pipe into the ground, knowing that the initial temperature everywhere is equal to 15 Celsius degree. And for tau bigger than 0, at the surface, we have minus 10 Celsius degree. So during winter, due to the snow cover, the surface at a certain time arrive at a temperature minus 10 Celsius degree. This snow cover is for 3 months. Okay, we know also the thermophysical property of the ground. Ragazzi, posso abbassarmi leggermente la mascherina? Okay. Grazie, tanto siamo. Okay, the thermal conductivity of the ground is 0.4 watt-meter Kelvin. The thermal diffusivity is 0.15 by 10 to minus 6 square meter second. Okay, observe at the beginning that when today we are analyzing cases that are transient cases. Both the Lambda system analysis and the semi-infinite solid are systems in which the temperature field depends on time. For this reason, I have to consider as thermophysical property also the thermal diffusivity of the ground. When I speak about transient problem, a property, one of the properties that is to keep in mind to be used is the thermal diffusivity. And we have to avoid, okay, here I have to finish this sentence at the beginning, to avoid the freezing of the water inside the pipe. So I repeat from the beginning the problem. I have a problem in which flows water, and I put this pipe inside the ground. I have to evaluate which is the depth to avoid the freezing of the water inside the pipe. Why I have the risk of freezing? Because after the initial condition of 15 Celsius degree everywhere, I have that for 3 months, the surface of my ground is at minus 10 Celsius degree. So I have to evaluate, the question is to evaluate the x. You remember that for a semi-infinite solid, I have one-dimensional case with axis only in the direction normal to the surface of the ground. So I have to estimate this x for which the temperature at that depth and after 3 months is equal to 0 Celsius degree. 0 Celsius degree is the condition in which I have the glass, so the solidification of water, the freezing of water. So for depth bigger than this unknown that I want to estimate, I'm sure that the water does not become ice, because for depth bigger than this value, the temperature will be bigger than 0 Celsius degree. The problem is clear for all of you?
Yes, Professor.
Okay, thank you. And
Yes.
Please, teacher, can you repeat the last phrase?
okay, I have to locate a pipe inside the ground for a certain period of time. I know that at the beginning this ground is at a temperature 15 Celsius degree. For 3 months during winter, I have that the temperature of the surface is minus 10 Celsius degree. According to the law of the semi-infinite solid, the temperature, also the temperature of the ground at different depth will change with respect to the initial condition, because it tends to decrease starting from the value of minus 10 at the surface, and then for other value inside the ground. I want to obtain which is the depth at which I have to locate my pipe, that after 3 months, so at the end of the snow period, reach the temperature of 0 Celsius degree. That is the freezing point. If at this depth, after 3 months, so after the long period of snow, the temperature is this one, means that if I put the pipe at a higher depth, so for x bigger than this value, I'm sure that I'm not freezing. It's better now?
Yes, teacher.
Yes.
Okay. And I have to apply now from the mathematical point of view the equation of my semi-infinite solid. So T for x 0, that means at the beginning is Ti, and for us is 15 Celsius degree. T of 0 tau, that means the temperature at the surface that we call Ts is equal to minus 10 Celsius degree. The law to be followed is T minus Ti over Ts minus Ti, wait, equal to 1 minus F of eta, with eta equal to x to a tau. You remember that eta is the similarity variable that we define to combine together the two independent variables x and tau, and to solve in a better way the problem. This one is also equal to Rc. So I can write that Tx tau is equal to Ti plus Ts minus Ti FC of what? Of x divided by 2a tau. Okay? Can I change? I wait a few seconds.
10 seconds, please.
Sorry,
Yes.
one moment.
Yes, yes, I wait. Questa era la 3, 1. Va. Now, Rc of eta, that is equal to T minus Ti over Ts minus Ti, is equal to, for us, 0 minus 15, and at the denominator minus 10 minus 15, equal to 0.6. Why I can use Celsius instead of Kelvin here? Because I consider temperature differences at the numerator and the denominator. It's better to repeat for someone. And now I want to, the unknown, what I want to evaluate is eta at the beginning. And then after, by means of a definition of eta, then I evaluate x. But how to estimate eta? I use the tables. Here I write a small portion of the table in the range I'm interested. This is a small portion of the table which express the eta, the ERF and the RC as a function of eta. My RC is 0.6, so is this one, is in the middle of the two values. That means that I have to interpolate I obtained that for me, eta is equal to 0.37. I hope that you know how to interpolate from a table. I hope. So, knowing the values of a table corresponding to the higher value of mine and lower value of mine, means that my unknown is here in the middle, and by interpolation I'm able to calculate that my eta is equal to 0.37, sorry. At this point I can write that x is equal to 2 eta, and substituting numbers, I have that 2 by 0.37 by square ratio of 0.15 . And here time was 3 months. So 3 months are 90 days by 24 hours by 3,600 seconds. Because as usual, you have to pay attention to units. And I obtain 0.8 meters. This is the minimum depth at which I have to locate il sole negli occhi, fantastico. Minimum depth at which I have to put my pipe to avoid the freezing of the water inside. Okay? It's okay?
Yes, Professor.
Yes, yes.
Okay. Okay, new example. Now, in this case, we have a thick black painted wood block. E chi più ne ha, più ne metta. Allora, the thick black painted wood block. Okay, that is at 20 Celsius degree. This block is subjected to solar radiation with that is equal to, so I have the block, okay, this is the block, and I have a solar radiation G, solar, that means on the block I have a net flux equal to 1250 watt divided by square meter. We have to determine the temperature at the surface after 20 minutes. Ts, my unknown is Ts, after 20 minutes. Okay, neglect the losses. And the system is this one. I imagine here I calculate here. Wait. I do another sketch of my system, better sketch. Okay. I have a block that I consider as semi-infinite solid. That means that it towards infinite in this direction, towards infinity in this direction, towards infinity in this direction. X is like that. And Ti, initial value of temperature, 20 Celsius degree. I have a net flux on the surface of my block, and I know the value of this QS. We call it QS. We have to evaluate the temperature of the surface. This one is Ts, that is the unknown, after 20 minutes. Two cases. Case A, wood, like the example suggests, for which K thermal conductivity is 1.26 watt meter Kelvin, and the thermal diffusivity is 1.1 by 10 to minus 5 square meter second, and case B, Kelvin, scrivo, wait, no. Case B, aluminum, in which K is equal to 237 watt meter Kelvin and A is equal to 9.71 by 10 to minus 5 square meter second. Okay, so I have to do the calculation for the two cases with wood and with aluminum. Aluminum, the pronunciation, but I'm not sure. Okay, this is a different case with respect to the previous one, because we calculated analytically the solution for the imposed temperature boundary condition. The analytical solution presented during the theory lesson was related to a boundary condition of imposed temperature at the surface. In this case, we have another boundary condition. In this case, the boundary condition is imposed heat flux, this one. So we can't apply the solution obtained during the lessons. And now I give you directly which is the analytical solution for that case. You are ready to change?
Yes, perfect.
Okay. Oh.
Yes.
The solution, analytical solution for imposed heat flux is this one. Ts, that for us is T of 0 time, is equal to Ti plus the heat flux divided by K multiplied by 4A tau divided by pi. This is the analytical solution for that new case, for which the boundary condition is not imposed temperature but is imposed heat flux. So now I have simply to calculate the Ts for hood, that is 20 minutes means this one is 20 minutes. 20 by 60. One hundred 149 Celsius. For the aluminum is equal to 20 plus 1250 divided by 237, and then square ratio of what? 4 by 9.5. 71, 10 to minus 5 by 20 by 60 divided by time. And I obtain 22 Celsius degree. So the value of the temperature at the surface depends on the type of material, considering the same condition and the same boundary condition. The temperature at the surface after 20 minutes depends on the thermophysical property of the material. Any questions? No? Now I change.
Oh, it's clear.
No.
Okay. We finish now this chapter and we start exercises of numerical methods. Okay, numerical methods. So in the file of the texts, you have a small chapter numerical methods. Now we start from the first one and we go on. And I have an element of a nuclear fuel. That is assumed as an infinite plane wall. So I can assume this element of nuclear fuel as a plane wall with, in Italian we can see lastra piana indefinita, che avrete sentito nominare 100 volte, la famosa lastra piana indefinita. Flat plate, and with thermophysical property K 30 watt meter Kelvin and A thermal diffusivity equal to 5.10 minus 6 meter second. The thickness is 20 millimeters, and this plate is cooled on both sides by convection with a H value equal to 100 watt square meter Kelvin, and T infinite, that is the fluid, the refrigerant fluid that cools this plate, 250 Celsius degree. Okay, the plate is like this one. I have an axis of symmetry because I have the cooling condition equal on both sides. And I know that starting normally, that means in usual condition, I have a generation of the power inside, uniformity generation inside the plate. So due to the nuclear reaction, is a nuclear fuel, due to the nuclear reaction, A gen, I call it 1 because it's the normal condition, is equal to 10 to 7 watt cubic meter. So I have a heat generation due to the nuclear fuel reaction equal to E gen 1 10 to 7 watt cubic meter. This is the basic situation. We have to analyze in particular a sort of not conventional operative condition for which suddenly this generation increase. So starting from E gen 1, suddenly we go to E gen 2, that is 2 times the previous value, 2 by 10 to 7 watt cubic meter. And we want to evaluate the distribution of the temperature, so the temperature field after 1.5 seconds of this sudden increase. So the temperature field, this is what we want to estimate. The temperature field after 1.5 seconds from the increase. We have two parts in this problem solution, because we have at the beginning to consider the steady state situation that we have normally. Normally we have this generation, and we want to estimate the steady state case for this condition. This steady state case obtained analytically, so 2 steps. The first one will be steady state for analytical solution for E gen 1. Step 2, transient numerical solution for E gen 2. So we have 2 cases. Steady state analysis analytical for E gen 1. Then I want to solve a problem from a transient point of view, because I have a sudden increase of this heat transfer generation for the second situation, that is E gen 2. Why I select analytical solution in one case and numerical in the other? Because steady state is simpler. I can really solve it analytically. Transient is not simple to be solved analytically, and I use the numerical approach. It's clear for all of you?
Yes.
Okay. So
Yes, Prof.
yes, we do the solution for we analyze first the first step. So the step 1, okay, this one. And we imagine to have a symmetrical shape of my temperature field. I have Ts on one side, Ts on the other side. The maximum will be in the middle of my plate. And I solve the problem. It will be a steady state one-dimensional case, because I assume to have only one x direction. I start the axis in the middle, and the axis of symmetry, because I know that I have a symmetrical shape. So I will wait. Okay. I will analyze the only 1/2 of the plate because the temperature field on the other side is absolutely the same. And now I want to start with the calculation that if I can change the slide. And analytical solution is this one. I have two. The two boundary conditions are x equal to 0, adiabatic boundary condition. X equal to L, T is equal to TS. This S equal to TS is not known, but I will apply, as usual, the energy balance for the 1/2 of a plate. So I will arrive to this point. So this one is only axis of symmetry, adiabatic. Perhaps symmetry want the y also at the beginning, I don't know. I'm not sure. Well, okay. And I start with the integration and I solve it, I apply to it the first boundary condition, and I obtain that C1 is equal to 0. I integrate again, I have that T is equal to minus E gen 1 divided by K, x to 2 divided by 2 plus C2. And by applying this second boundary condition, I can write that C2, wait, C2 is equal to TS plus E gen 1 divided by K, L to 2 divided by 2. Wait, because here in my paper I have, yes. So I can substitute and I obtain that, I can solve it this way, T minus A gen 1 divided by 2K x to 2 plus TS plus E gen 1 by L to 2 divided by 2K and is equal to TS plus E gen 1 by L to 2 divided by 2K, and that multiply 1 minus x to 2 divided by L to 2.
Excuse me, Professor. I don't understand this step. Can you explain me again?
Yes, what do you not understand? I have integrated one time. This one is the first integration. And to find the C1, I apply the red boundary condition. Then I integrate again, and I have another constant to be obtained. And I obtain the second constant by using the second boundary condition. I substitute this value of C2 inside the equation, that was this one, and I obtain a general formulation for T. Okay, you are right in the sense that at this moment TS is not known. TS is not already known. We have to estimate the TS. It's better now?
Yes, Professor.
Okay. And to evaluate TS, we can, as usual, consider an energy balance for 1/2 of my plate. And in particular, I remember to you the plate. We consider only 1/2 of the system. This is L. I call it this one L. And I can write for this 1/2 of my plate, I can write E gen 1, that is watt for unit volume, by L, by 1 by 1, considering a sort of volume with side 1 and 1. Yes, okay. We consider for unit volume generation is equal to the transfer rate removed by convection from the fluid yes, for the same area. The area at which we have convection is this one. Okay, because I have here H, the infinite. And this one is clear. From this one, I solve for TS. And I can obtain that TS is equal to T infinite plus E gen 1 by L divided by H. I substitute this TS here, and finally I obtain T equal to T infinite plus E gen 1 by L divided by H, point E gen L at gen 1, obviously. Wait, I write better. Not so better, but you might. And to 2k 1 minus x to 2 L to 2. This is the law that I wanted to obtain. This is the analytical solution for my steady state problem. It's clear up to this point?
Yes.
Yes, Professor.
What means analytical solution? Means that this solution allows us to estimate the temperature field everywhere. Everywhere means in all the points that I want. Obviously, for all the x value, because for us, here T is Tx. Tx as a function of x steady state is evaluated. Why I need to solve the problem analytically at the beginning? Because the real final aim of this example is to estimate, you remember, the temperature field inside the plate after the sudden increase of my volumetric heat generation. And I want to solve the transient problem. Now I change the slide. 5.2. I want to solve the next problem that is regulated by this law. I have to solve this equation. This is a transient analysis, analysis, and it's not simple to be solved analytically. We are not able to solve it analytically, and we want to have the approach, numerical approach. The previous analytical solution, it's important for us because when I have to solve a transient problem, you know that I need an initial condition. The initial condition of this second transient problem is the solution of the previous case. So the initial temperature field for my transient analysis is nothing else the temperature field of the steady state case with the previous generation. Okay? It's clear this point because this is the physical meaning. Then our mathematical step and solution and so on. But I want you to understand the sense. Now,
Sir?
yes.
I'm sorry. Do you mean the previous situation is initial condition in the the change of the situation? You mean am I right?
Yes, yes. Now we are at the step 2 of the analysis. We want to analyze transient problem with a Gen 2.
Yes.
And we need an initial condition for this problem because it's a transient problem. Which is the initial condition for this transient problem? Is the temperature field when the Egen was the value 1.
Yes.
Before the sudden increase. That means the solution obtained before. Okay, now I use the explicit method, sorry. Numerical approach. Explicit method. And the equation can be approximated in this way. Now I try to go slowly to avoid mistake in the writing, otherwise for you it's very difficult to understand. So I go a bit. Okay, this is the equation, but is nothing else. So this one is nothing else. This one, but written with a numerical approach. And this approximation using the explicit method, what means the explicit method? That the only unknown is this one. For each equation, the only unknown is this one, because I use the forward difference form for the time derivative. And this equation is for the interior nodes. I rearrange this equation, now I do some mathematical steps, introducing also the Fourier number. You remember that this superscript means time and the subscript means the space, okay? And m I plus 1. Okay, finish to copy and then I change. Okay, you have finished or not?
Yes, I finished.
Okay,
Yes,
I wait for someone in class. Now, if you remember, I have to solve for the only unknown, and the only unknown is, as previously specified, is this one. I have to solve for it, that is our unknown, because the explicit method allows us to solve this equation, to have one only unknown for each equation, and the unknown is this one. I go to the next. Okay, so Tm I plus 1 is equal to Tm I, but multiply 1 minus 2 delta Fourier plus delta Fourier, but multiply Tm plus 1 I plus Tm minus 1 I plus again delta x to 2 divided by k, and Now I have the equation, I repeat, for the interior nodes. I want to now select the mesh. I want to properly select the mesh. And I take again my half portion of the plate. And the X was here. The 0 was here. And I take 5 intervals. I divide my axis X into different nodes. I identify 5 intervals for 6 nodes. 1, 2, 3, 4, 5, 5, sorry, 5 and 0. Okay, sorry. So 6 nodes with delta X. Delta X is equal to 0.01 divided by 5 and is equal to 0.002 meters, equal to 2 millimeters. So applying a numerical solution, I will find the temperature only each 2 millimeters, not in all the points that I want in my plate, only for 2, 4, 6, and so on millimeters. This is the limiting of applying a numerical solution. And this equation is for nodes 0, 1, 2, 3, and 4. Not for the node 5. Now we have to find the equation for the node 5. For node 5, that is on the boundary, we have to consider this sketch. It's a sort of zoom of the previous figure. This is node 4, this is node 5. Here I have convection. And I write that, I have to write, as you remember, the energy balance associated to this node volume. The node volume, so the small volume associated to the node 5 is only this one, that has thickness delta X divided by 2. I have to write the energy balance for this light blue volume. For the volume of node 5. And this energy balance is it flux from right. It flux from right is convection from right plus it flux by conduction from left, Fourier law. The distance between the two nodes is delta X, plus generation of the volume. The volume is only 1/2. Equal to, we are in the transient analysis, energy content variation in time of my small volume. Qua si capisce? Si legge? Wait. 1 plus 1 T5 I divided by delta tau. This
Sorry.
is, yes.
Only one question. Egen is Egen 1 or 2?
Gen 2. Always,
Okay.
from the beginning, I neglect the 2, but is always, for all the cases, is 2, because we are in the case with Gen 2. Also, previously, I neglect these 2, because otherwise, too much, you have too much to write, you can confuse, especially if I'm writing here. But it's Gen 2. Okay? This point is clear because this is the interesting point, how to write this energy balance. The other steps are mathematical steps. Ci siete? So, we introduce the Biot number also for this case, because now we love the Biot number at this point, and so the Biot number is H delta X divided by K. And we can solve this equation for the only unknown. Also, this equation is written in an explicit approach. And the unknown is this one. So, I write for the unknown and I find finally T5I plus 1 equal to T5I, that multiply 1 minus 2 Biot by delta Fourier minus 2 delta Fourier plus 2 Biot that multiply delta Fourier that multiply T infinity I plus 2 delta Fourier by T4I plus delta Fourier E gen delta x to 2 divided by k. Okay. Okay, so we have now all the equations for all the nodes. We have 5 nodes and we have 5 equations. Sorry, we have 6 nodes, sorry, and we have 6 equations. 5 equations of this type for the interior nodes. And the equation written here, or here, better, here, for the node number 5. We have, if you remember, when I use explicit method, I have to check the stability. And which is the manner to check the stability is to verify if the coefficient of the unknown at the previous instant is bigger than 0. So what I have to check is that this one is bigger than 0, bigger or equal to 0, and also this one is bigger than 0. Can I change slide, page?
No, sorry. Can you repeat which terms have to be positive?
This one and this one.
Okay. Sorry, I have not seen the.
Vedete a casa? Vedete il foglio a casa, vero?
Sì, lo vediamo. No, non avevo visto il segno verde in alto a sinistra, scusa.
Ah, ok, scusa, ok, va bene. And and now I have to consider delta Fourier less than 1/2 for the first imposed stability condition, and I have that delta Fourier less than 1 divided by 2, 1 plus Bayeux number for the second. So these two are the green previous slide condition bigger than 0. So the Bayeux number for me, for my case, the Bayeux number is equal to h delta x divided by k. That is 1100 by 0.002 divided by 30, and is equal to 0.0733. At this point, we have already selected the mesh. Okay, so we have already selected delta x, that is the mesh. We have to impose a limitation in the time. Is substituting this number of Biot here, I obtain that the delta Fourier must be less than 0.466. That is bigger than this 0.5. So the Bayeux number must satisfy both the condition 0.5, that is this one, and what I obtained from the second boundary condition, from the second limiting condition. And now I have to find the limiting for the time. And remembering the definition of the Fourier, delta Fourier is equal to a delta tau by divided by delta x to 2. I obtain that delta tau, that is delta Fourier by delta x to 2 divided by a, is equal to 0.466 by 0.00222 divided by 5 by 10 to minus 6 equal to 0.373 seconds. So my delta t, the delta tau, sorry, t, okay, my delta tau must be less than 0.373 seconds. This is the limiting value of the tau time to avoid the stability, to avoid problem of instability. Okay? So, for example, I select delta tau equal to 0.3 seconds. I can select the time step less than this number. Okay?
I'm sorry, Professor. Could you please read the last sentences? I can't.
Okay. So we have to apply the two conditions on the delta Fourier. And simply, I find that the delta Fourier must be less than 0.466. Remembering the definition of a delta Fourier, I find a limit on the delta tau, that is the time. And I find that my delta tau must be less than 0.373 seconds. So I can select, for example, a delta tau that is 0.03, that is less than 0.373 seconds. Okay? This is my selection, as the mesh is my choice, the time step, is enough to check if it is less than this number. Okay?
Okay, but and you wrote then, I can't understand it after that.
To avoid instability. Thus I select, for example, delta t.
Oh, okay.
Thus è come dire so.
Yes, professor. Thank you so much.
Okay.
Sorry, Prof, but if delta Fourier was more than 0.5, we would, if delta Fourier was more than bigger than 0.5,
okay,
we would change delta x, our mesh, or not?
But okay, we can act on both delta x and delta tau, but after doing the calculation or the analysis fixed at the mesh, we change better the time step. We reduce the time step.
Ah, okay, no, yes, thank you.
Okay.
Yes.
I can change the slide. No, now the problem is solved because we have checked the stability, we have selected the time step, we have selected the mesh, we have all the equation, and we have simply to solve step by step the system of equation. So I simply now write for you the table of the solution. That is a bit boring activity to copy this table, also for me, but is what we have to finally write. And I have I is the time step, which correspond to t tau in second, and temperature 0, temperature 1, 2, T3, T4, T5, and T6. Exactly. And the time step we consider is 0 at the beginning. This 0 means steady state so the situation 0 means the solution of the previous case, steady state for Egen 1 for time 0. Then I have an instant 1 that is for 0.3 second, at time 2, 0.6 second, at time 3, 0.9, at time 4, 1.2, at time 5, 1.5, and then infinity. Infinity means, again, steady state for Egen 2. And now I have, this is steady state in the second condition, in the second situation. And now it's a question of copy. It's boring, I know, but we finally...
Prof, why also T6?
Dov'è T6? Ciao, buongiorno. Ah, ok. Perché why T6? Where is?
No, the last column.
No, so see, is my okay. I'm tired. Is because the professor at this moment is tired and invent a point that does not exist. And thank you. But it's not so important that now we write all the points, but it's only to, okay. We can write also Okay, and so on. We can also write, okay, and so on, some number like that. Then if someone is interested in this solution, I can give you numbers. I can write here at the bottom the last row that refer to the steady state.
It's done by monthlies.
Yes, by computer, by MATLAB, by our software, not manually, because you have to solve the problem for each time step. Is an explicit method, so it's easy to solve because for each equation you have only one unknown, and you can find directly the value. But you have first for the instant 1, for the instant 0 to solve the system, then for the instant 2 again, and so on.
It's not easy to solve it by hand.
No, it's boring. No, and this one is okay, and numbers, not so interesting. Okay, the interesting point is that I have values for the time step 5, 1.5 second. I write only this row, but because it's interesting. Okay, if you observe the temperature field after 1.5 seconds, that was what I wanted to obtain. The problem asked to me the temperature field after 1.5 seconds. So exactly this time field, this temperature field. This temperature field is far from the steady state. You look at the numbers of this row in light blue are different than the steady state for eGen2. That means that I'm far from the steady state condition after 1.5 seconds. Stop. For today, if you have no question, we stop and we finish exercises of this part next Monday, and we start also with the convection. Any questions? Lo so che state tutti copiando.
No, thank you.
Ok, bye. Vabbè, questo posso anche.
Thank you, Professor.
Thank you, bye.
Bye.
Thank you, Professor.
Thank you, Professor. Bye-bye.
Bye bye.
Thank you, Professor. Bye bye.
Thank you, Professor. Bye. See you next week.